Hello and welcome. My name is Yildiz. I'm a research associate at the National Green Infrastructure Facility at Newcastle University. I will be presenting our work on the potential for ground source heat exchange in green infrastructure on behalf of my colleagues Dr. Stirling and Professor Glendenning. Let's start with why we want to monitor the thermohydrological behavior of green infrastructure. The efficiency of ground source heat pump systems, utilizing either deep or shallow ground heat exchangers, is controlled by the thermal conductivity of the soil they are placed in, which is a function of soil type, mineralogy, porosity, and water content. There is much evidence in the literature that efficiency is affected by rainfall for the shallow exchangers and groundwater for the deep exchangers. An increase in water content results in a higher thermal conductivity, which in turn provides a more efficient heat transfer. As shallow exchangers are buried in trenches and covered with a certain backfill material, the variation in the efficiency is directly related to the hydrological changes in the soil. In other words, the atmospheric boundary conditions are crucial in determining the heat transfer. Artificial ways of increasing the water content of the trench for higher efficiency have been proposed. However, none of these are as advantageous as installing in green infrastructure. Let's have a look at the concept of the combined system. Co-locating green infrastructure and ground heat exchangers in urban areas has several benefits. Firstly, you do not need to dedicate space only to accommodate the exchanger, and it can provide an enhanced bioremediation. And lastly, there is potential for more efficient heat transfer. Green infrastructure is built to accommodate incoming rainfall and runoff, and it's expected that its substrate will have a higher water content and in turn higher conductivity, thus giving an opportunity to have a ground source heat pump system with increased efficiency. In order to test the heat rejection into green infrastructure substrate, we have built a large-scale outdoor Lysimeter setup at the National Green Infrastructure Facility. A 1.8 meter diameter soil column was built using an 800 mm high sand layer covered with 150 mm of topsoil. A heating cable was placed at 850 mm below the surface to simulate the heat rejection from a shallow ground heat exchanger. Conventional meteorological parameters are measured directly above the Lysimeter, and drainage from the soil column is recorded using a follow gauge at the base. We monitored various parameters at multiple locations, and these can be summarized as volumetric water content and matrix suction, soil temperature, thermal conductivity, and heat flux. Now, let's have a look at the monitoring data. We start with the meteorological parameters. Daily rainfall, air temperature, relative humidity, and net radiation are presented in this figure. An increase in the mean air temperature is evident over the monitoring period. We can see 2 heavy rainfall events in mid-June, and we can also see that days with high relative humidity coincides with days of low net radiation. Furthermore, if we subset the data for dry days and wet days, we can see that wet days had a higher relative humidity and lower net radiation. These parameters were then used to estimate the potential evapotranspiration. By combining the rainfall, evapotranspiration, and drainage, we can observe the days with a net inflow or outflow. The net water balance governs the hydrological regime of the soil column. Here we see how the volumetric water content changes within the sand layer at 250, 350, 550 and 750 mm below the surface. A general reduction in water content over time can be observed at all depths. The heavy rainfall events cause a sharp increase at shallow depths, whereas the changes are rather smooth for deeper layers. These variations in water content are reflected in thermal conductivity, which follows a very similar trend in time and depth as the volumetric water content. Similarly, the same reduction in thermal conductivity over time is evident at all depths, and the response to heavy rainfall is more significant at shallow depths. By using the simultaneous measurements at various depths, we can obtain a field thermal conductivity dry-out curve, which defines the relationship between thermal conductivity and volumetric water content of a soil. Thermal conductivity decreases with decreasing water content, and the slope of this change increases around 5 to 6% volumetric water content. Establishing this relationship enables us to develop coupled modeling frameworks. Lastly, let's have a look at the soil temperatures. We see that the diurnal variation of the air temperature affects soil temperature of the shallow layers. This is evident in the contour plot, and also by comparing the difference between the maximum and minimum temperature in a day in the figure on the right side. Here we see the mean value for the difference between the maximum and minimum temperature in a day is around 7 degrees for air temperature, whereas at deeper layers this goes around 0.5 degrees. So deeper layers do not experience significant temperature fluctuations within a day. We also see that extended warmer periods or cooler periods propagate a temperature change within the soil column, albeit with a clear lag. To conclude, we have demonstrated that thermohydrological conditions within an engineered green infrastructure component are conducive to efficient ground heat exchange. The substrate maintained high thermal conductivity states even under summer conditions. The monitored soil-water atmosphere interaction has illustrated the highly thermohydrologically coupled response of a functioning green infrastructure component. And lastly, such co-located systems have the potential for significant mutual benefit in terms of environmental and economic performance, leading to a more attractive proposition for sustainable water energy approaches in urban environments. Thank you very much for tuning in. These slides are available online, and you can also watch how we commissioned the Lysimeter setup on our YouTube channel. If you want to read more about this work, please see our latest publication in Geomechanics for Energy and the Environment. Thank you.